today. And today I think we have kind of a fun topic, really. Makes you think a little bit about infinity, which we're going to talk about more this semester. Calculus kind of fun like that, and math in general uh, gives you a way of really analyzing the universe and the way things work with some kind of spectacular results from time to time, right? That's why we think about all right. So here's today. It's not that exotic. It's improper integrals. I think you'll still find these are fun, especially by the time we get through next time. I may not finish these today, I think, but the homework's not due till Friday. You get started. And what's an improper integral? There are different kinds. I want to just introduce it by an example. Suppose I had to integrate from 1 to infinity a function 1 over x squared dx. Well, how do I do that? Actually, you could try just finding the antiderivative, plug in infinity and 0, and get it. What you mean precisely when you do that is you're thinking of, what if I just took the integral from 1 to b of 1 over x squared dx, right? Well, now I'm talking about this. Here's the function of 1 over x squared. Maybe it looks something like that. And there's another piece over here that I didn't draw. And here's x equals 1 here, maybe. And so I'm talking about finding the area under the y equals 1 over x squared function there. And I could integrate from 1 to any finite point b, because we already know how to do that, right? This is a continuous function on a closed interval. We know, right? That's one of the reasons we defined continuous last semester. There's all sorts of theorems that say if f is continuous, then, and one of them is if f is continuous, like this function is, then its integral from a to b exists on an interval where it's continuous. So this will exist, and we already know a formula for it, right? But now, wait a minute, that's only an estimate. I cut off all this area. Well, maybe I'll make b a little larger, right? Put it out here. This is a little better estimate. Well, maybe I'll put it out further out here, way out here. Maybe I'll put it out at 1 billion. Maybe I'll use one of my numerical methods and estimate it. But I'll put it out here. No matter how far I put it out, it's well defined. What if I just define this then to be the limit as b goes to infinity of this sequence of integrals? I go from here to here, from here to here, from here to here, and I'll just let b go to infinity. We'll define that. I won't write define yet, to be the integral from 1 to infinity. We'll take the integral from 1 to b and let b go to infinity. And so now we know how to do this one, right? Because 1 over x squared is actually x to the minus 2, and we can use the power rule. We'll say 1 over x to the minus 2 has integral x to the minus 1 over minus 1, right? And we have to plug in b and plug in 1 and subtract according to the fundamental theorem of calculus, right? We can evaluate a definite integral, the one with the endpoints, by taking the indefinite integral and arbitrary antiderivative, plug in the top endpoint, plug in the bottom point, take the difference for any continuous function, right? All right. So now what do we do? Well, this is just a function minus 1 over x, right? So what I'm going to do is take the limit as b goes to infinity of minus 1 over x, plug in b is minus 1 over b. Subtract minus 1 over 1, plugging in 1. I always hate those double minuses, right? I tell people it's like, tell your mom it's not the case. I'm not going to the movie today. That's, it always throws things off a little. But that's what happens here. All right, so limit is b goes to infinity plus 1 minus 1 over b.
I'm confused, right? I'm working on this fashion show.
Well, limit of a constant is the constant 1. And limit 1 over b, b is getting larger and larger. Remember from last semester that limit is 0. So this whole limit is just equal to 1. This is actually unit area under here.
Are you leaving, Carson?
That's the proof.
No, is that where you're going?
Right?
Are you coming back? Are you coming back?
Well, I have to practice.
Have a comment online? I
Are
can't
you
hear
coming back, Carson?
this up. Was there a comment? I'm sorry. Okay. I could barely hear something on there. I had my sound down. All right, so that's the concept, and now we can make that rigorous, right? We'll just make that same definition for but I just want to point out first, I'll do one for example. Suppose I had the integral from 1 to infinity of 1 over x with respect to x. What would that give me? I just follow the same thing and say, oh, that's the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. Again, this is a closed interval where the integrand is continuous. So I can say, by the fundamental theorem of calculus, is the antiderivative of 1 over x, namely natural log of x. I can leave off absolute values because it's on a positive interval. Plug in 1 and b and take the difference. So it's limit b goes to infinity, ln b minus ln 1, right? Remember ln 1? Yeah, 0, right? So this is just limit b goes to infinity, natural log of b, and that's infinity, right? So this integral actually is infinity. We sketch it here. Y equals 1 over x is this branch of a hyperbola, right? There's two branches here. You plot it. You learn this one in algebra. If I take its area from 1 to infinity, this thing here, that's infinite. The idea being if I go from 1 to b, I get a certain area. If I go 1 to another further b, I get another area. And these areas, if I keep looking, I get unboundedly large. By going far enough, I can make this area under here as big as I want. So the limit is actually infinity. You know, 1 to b is ln b. It gets bigger and bigger without bound, right? Some of these can have finite area under here if they drop off fast enough. 1 over x squared drops off fast enough, but 1 over x does not. It's got infinite area underneath. So in general, we're going to make this definition then. That's what we wrote here. We're going to make a bunch of definitions. And proper for all is an integral that just has an infinity somewhere in it. So this is the first case. Here, if I have the top endpoint is infinity, and I go from some fixed point A, f of x dx, we'll say that that is equal to the limit as b goes to infinity of the integral from a to b of f of x dx. Easy. That's what we did in those last two examples. Just take b bigger and bigger, and think of all those integrals. The limit. Just let a go to minus infinity, and take the integral from a to b, f of x dx. So that'll be the definition of the improper integral. Then there are others. Yeah. Of f of x is infinity or minus infinity. The function gets bigger and bigger without that. Suppose I go with the function a to b, and there's an asymptote here. Maybe it goes up to plus infinity like that. I want the area. What's that area? Again, there's a and in this case, we say that the will be limit as x approaches as c approaches a from the right of the integral from c to b f of x dx. Fine, I can write any point c here over to b. Oh, sorry. 1 minute. Let's do the same. Where infinity is the right endpoint. Yeah, the limit as x approaches b from the left, going to a finite endpoint b, is infinity or minus infinity. Then we'll define the definite integral, call it an improper integral, the definite integral from a to b f of x dx. Where now you've got this kind of case. Maybe it goes down to minus infinity this time. It doesn't matter. A to b, and maybe we've got an asymptote like that that's going down to minus infinity. So if that's y equals f of x, now the definite integral is no longer the area between the curve and the x-axis. What is it we're finding? On the x-axis, it gives you the area below the curve. But if it's below the x-axis, then what you're adding up in this, here's the definition of the definite integral, right? This is how it's defined. It's the limit as the number of rectangles goes to infinity with tacitly assumed in here 0. Sum k equals 1 to n. There's n rectangles. F of x k star, the height of some k star, held x k width. Height times width. We're adding up all these bunch of little rectangles there. But if f is negative, then you get minus the areas below. So that's in relation to areas. It's the area when it's integrable and the function is not negative. This one I'll give us minus the area since it's negative on this interval. But what about this thing? How shall we define it when it goes down to minus infinity? How will we get minus the area from this integral? We'll say, just like we did here, we'll take the limit this time as c goes to b from the left of the integral from a to c, f of x dx. All right, with the idea, we're going to go from a to some intermediate point c. We can do this integral because this right, function doesn't have it here. And then we'll go to c a little further and c a little further. And the limit, we're going to find that to be the area under there. So that'll be. In the fifth case, there's actually more than 6 cases, but I'm only going to put 6. You can kind of figure out. What if there's an infinity in the middle of the integral? Right? What if f of x approaches infinity or minus infinity as x approaches an intermediate point c from the left or approaches c from the right or both with c between a and b? And I'm interested in the integral from a to b. Remember from calculus 1, if you wanted an area under the curve, right, from a to b, you could take the integral from a to c, add it to the integral from c to b. We're going to say this one is the integral from a to c, f of x dx, plus integral from c to b, f of x dx. Genius, right? Because I just have to. This puts it in. You want to integrate from a to b, and maybe it goes up to plus infinity here, huh? Maybe it goes down to minus infinity here. So the integral is going to get this area, and then plus minus this area, right? Areas always, but the definite integral here minus the area down here. If these are actually You can integrate from same area. Any questions on that? One of the reasons I think to stop doing the videos if nobody needs them. But this little tiny board, I have to erase it real fast. All this stuff will be erased now. But all right. Some departments don't mind that. They have just little tiny boards up front. If you got a athletics department or nursing, I don't need to write all that much up there, but we have to write a lot here. So. All right, here's the last one I'm going to put up. If I have an integral from minus infinity to f of x dx, how shall I define that if both? Right, so an improper integral, you can either have an infinite endpoint, one or the other or both, or you can have an infinity as an endpoint on a finite interval, because the function goes to plus or minus infinity, or you can have an infinity in the middle of the interval. Those are the improper integrals. This one will be defined this way. We'll again make this rule carry over. We'll say it's the integral from minus infinity to c f of x dx plus integral from c to infinity f of x dx. This same rule carries over with c any intermediate point. So follows calculus 1. How nice. We don't have to learn anything more. But it also works well, right? To see any intermediate point, any finite point, I guess I should say, any finite number. And regardless of how you do it. So if I have a function like this, I want to know its area. How can I do it? I stop wherever I want at c here, and I'll take the integral from minus c on. Yeah. Uh, so the definition. Improper integral. What do we say? The integral diverges, or is divergent. If it's a finite, then we say it converges. Sometimes it's nice to say it the other way. It converges and diverges. You got to find it. It converges. You get anything else, infinity minus infinity, nothing. Then it diverges. Here's the kind of case they cook up. I think this is one of your homework problems, as I recall. Suppose I hit the integral from 0 to infinity of sine of x dx. There's an improper integral for you, right? What am I calculating with that? Right, nothing. So here's what you get. You think of it as an area problem again. That's intuition is terrific here. Right? I say that Einstein made imagination is more visualize this stuff uh, for that reason. Because what happens is, if suppose I integrate from 0 to pi here, where the sine function crosses the x-axis, and I want to find that this integral. This integral is the sum of the areas above the x-axis minus the areas below, right? Because over here it's getting minus the area, and over here it's getting plus the area. So this has some finite area, but by symmetry, this is the same. So if you integrate from 0 to pi, you get this finite number. If you integrate from 0 to 2 pi, you get 0. Integrate to here, now it's that same finite number you get back to pi. So 3 pi is the same value as pi, but 4 pi is back to 0, right? So it oscillates. The integral is going up and down, up and down. If you take the limit as b goes to infinity of the integral from 0 to b of sine x dx, well, its value is sometimes positive and sometimes 0 and sometimes positive, sometimes 0. You simply say it does not exist. Oh, we say it diverges. That's usually what we say instead. Right? If the limit doesn't exist, we'll say it diverges. Here's a fun one. This has a whole bunch of interesting things in it. Yeah.
Okay, so it diverges because we can't really say who's going to break down to a cosine. The limit is cosine goes to infinity.
Yeah, its limit as b goes to infinity. Minus the cosine x. 0 to b, which is minus cosine, limit as b goes to infinity. We'll just go ahead and work it out. Limit b goes to infinity of minus cosine b minus a minus cosine 0 is plus 1. So it's the limit as b goes to infinity of 1 minus cosine b, but this oscillates up and down. This is telling you the area from 0 to this point. And so this oscillates between plus and minus 1. And so the area is going between 0 and 2. When you're here, it's 2. When you're here, it's 0. When you're here, it's 2. When you're here, it's 0. And so since this does not exist, we say the integral diverges. That's the idea. Okay, here's a fun one too. What if I wanted to evaluate the integral from minus infinity to infinity of 1 over 1 plus x squared? Some of these are, one of the nice things about this section too is a lot of these are intuitive. If you just take the antiderivative and take the difference, you can kind of see what it is anyway. Or we're just trying to be be rigorous. Experiment here. If it's true or not, that means you have to have a real definition for everything. So we wrote it out. Now we know when we write this. The integral from minus infinity to whatever point c I want, 1 over plus x squared, plus integral from c to infinity of 1 over 1 plus x squared. It doesn't matter what I choose c to be, so I'll choose an easy number. Yeah, there we go. Get 0. So I integrate from minus infinity to 0 and 0 to infinity. That one. Or any other. What's the integral of 1 over? Let's find out the definition of it. This has the of the integral from a to 0. This one has infinity at top end point, so we'll take the limit as b goes to infinity of the integral from 0 to b. All right? There's the definition. Now, what's the integral of 1 over 1 plus x squared? We call this arctangent, right? The limit as a goes to minus infinity of the arctangent of x. Plug in 0, plug in a. Fundamental theorem of calculus. What that is? Because if you want to evaluate a definite integral of a continuous function, you can take any plug in the bottom one, take the difference, right? Yeah. Then we have plus limit p goes to plus infinity of the integral of arctangent x taken at b taken at 0, subtract. Well, let's see, its limit a goes to minus infinity. Tangent of a. Plus limit b goes to infinity. Arctangent b minus arctangent 0. All right, so I guess this. I'm going to see if this is working properly. I hope so. So the arctangent 0 is 0. We can drop those off. What is the limit as b goes to infinity of arctangent b? Anybody know that one? Need to know a few of these kind of things for the homework, actually. This one's on there. Yeah, here's how you can figure it out. Remember the graph of arctangent. It's like that. That sound familiar? Yes? No? It has this asymptote, y equals pi over 2. It has this lower asymptote, y equals minus pi over 2. Nobody remembers that? Here's how you get it. Remember inverse functions from algebra? You use it for algebra and trigonometry. The tangent function, everybody knows that one, right? Looks like this, and then it repeats. This is y equals tangent x. Goes from minus pi over 2 to pi over 2 to complete one period. And it looks like this, right? It has these two asymptotes. I guess that's where those asymptotes. But how do you find the inverse of it? You take it, flip it over the line y equals x with the idea that if AB is on here, you flip it over, interchanging y and x, and you get the point BA here. That way, when you take tangent of A, you get B, and then you take arctangent of B, you get A back. Flipping over the line y equals x, so that AB becomes BA, makes the inverse function that undoes it. Arctangent undoes tangent. But what that means is that the shape of arctangent is exactly the shape of tangent. It's just flipped over the line y equals x. Interchange the two axes. If this has asymptotes plus or minus pi over 2, so does arctangent. Y equals plus or minus pi over 2 because you switch the axes. That's inverse function. Now, you this, but they didn't teach you in algebra and trigonometry. What does it mean that y equals arctangent x has an asymptote pi over 2? Absolutely, yeah. This is here. Tangent is pi over 2. The asymptote is that the limit of the function is that number. You don't define that. Algebra, you say, oh, look, it's getting closer and closer. Science, science teacher doesn't want to prove it. That's the way you believe them. Anyway, we have to do that a little bit here. Your calculus book is so thick, it's a tome. You see the new free ones that you can get online? It's not a bad idea if you don't like your textbook ever. What are some of the ones? Like there's LibreText has one. OpenStax. OpenStax has a 3-volume calculus set. But calculus is really complicated, is what happens out of there. But anyways, we'll get back to this. The what they don't tell you in algebra, because they have to sing and dance instead, is that this thing, when it has an asymptote, that means that's the limit. So the limit is b goes to infinity because this has a horizontal asymptote towards infinity is pi over 2. What's more, the limit is a goes to minus infinity. That's not very clear, is it? Minus infinity. Is this one minus pi over 2. And that one, I'm taking minus the arctangent, so it's minus pi over 2 plus pi over 2. Amazingly, the area under this curve is pi. If I take what I found is the area under the non-negative function y equals 1 over 1 plus x squared. 1 over x squared function. Exactly. It's going to come out pi. It's kind of amazing, isn't it? We're going to get a lot of stuff like that this semester where things come out with a pi, strangely. But you use the arctangent function to prove it, right? Then thing is that. Poor high school history teacher, we kept having him tell us stories and we never learned anything like that. All right. Yeah. Here's suppose I give you this example. Integral from minus infinity to infinity of 1 over 25 plus 9x squared. This is a homework problem here. This or one just like it with different numbers. How do I do that one now? These are squares, I think you're saying. It looks like the last. Think about it. What if I took and substituted 25 u squared equals 9x squared, for instance? So the 5u equals 3x and 5 du equals 3 dx by taking the derivative dx over here and derivative du over here. That says dx can be replaced by 5/3 du. Right? 9x squared can be replaced by 25u squared. And this becomes over 25 plus 25u squared times 5/3 du. I pull out. And I've got a duck, right? 1 plus x squared, but u squared. We know that one, right? It's just a different variable name, but it's the same value, right? Because dummy variable, it doesn't matter. It falls out when you evaluate at the endpoint. And just to point this out, as x goes to infinity, 3/5 x goes to infinity. So this endpoint is still infinity. As x goes minus infinity of 3/5 x. What is that? Oh, it's minus. As x goes to infinity of the top endpoint infinity of 3/5 x. That's u infinity. So u goes. There it is. Pi. Right. So this is actually 1/15 pi. This one. But you can do that like that. Just recognize it looks like something you've seen before. Now, maybe the most important topic today. I told you that Einstein quote. This is where you need to have some imagination that really helps you. That the formulas are important and all, but the intuition here is absolutely key to doing some of the later chapters. This is going to come up again in one of the later sections when we do infinite sums, which are also very fun. Suppose I have this one, the integral from 1 to infinity of 1 over x to the p dx. Well, I wonder what that one is, where p is an arbitrary positive number, let's say. What could that be? An improper integral, right? It just has this definition. Limit as b goes to infinity, integral 1 over x to the p from 1 to b. And 1 over x to the p is just x to the minus p, right? Cool. Like this is, let's see, x to the minus p plus 1 over minus p plus 1. If p is not equal to 1, p equals 1, I get division by 0. Instead, when I'm integrating if p equals 1 is 1 over x, that comes out to be natural log x. So this is the power rule. I leave off the well, I need the limit. Oops. And then this has to be plug in 1 and b in both of these. So I have the limit as b goes to infinity of either, if t is not equal to 1, plugging in b minus b to the minus p plus 1 over minus p plus 1, or see, I plug in b and subtract. I forgot to subtract 1. Minus 1 over minus p plus 1. That's if p isn't 1. If p is 1, then I have the limit of ln b minus ln 1. And ln 1 is 0. Is infinity. So this bottom limit's going to be infinity when p. One over come out to be 1 over minus 1 if p is this term minus over p is positive power of infinity. This goes to infinity. And so you get p less than 1. This is the intuition rule for the whole section. That's a very important concept. Because what does it tell you? There's a if p is at least as big as 1, then the function 1 over x to the p is dropping down fast enough, like p equals 2. You get apply 1 over 2 minus 1 is 1. Or less than 1. And it doesn't take the rule. The function has to drop off faster than first. So you can now do problems like this. I'm about out of time, so I'll just have to do this quickly. We'll have to finish this next time, but you can start on some of these. What if I wanted to integrate from any finite number to infinity? We'll do 1 to infinity just to match this, but integral from 1 to infinity of 1 over x to the 0.999. What does that give me? 1 over x to the p with p less than or equal to 1, so it's infinite. It diverges. Right? It's not a number either because it's infinity or minus infinity or no number, you say it diverges, right? But what if it's integral from 1 to infinity of 1 over x to the 1.001? That's the other rule. 1 over 1.001 minus 1 is 1 over 1,000 is 1,000. What happens is p gets real close to 1. This integral gets bigger and bigger and bigger. When p hits 1, it first becomes infinite. If I put x to the 1, then I'll get, I make this number real big by putting p close to 1. That's what it's telling you. You need to have the 1 over x to p bigger than 1, and then it will converge because it has a finite number. Guess I'm out of time. You can now use this to compare other integrals and decide whether they converge or diverge, even if you can't evaluate the integral. You say, oh, that just diverges because I'll compare it with 1 over x to the whatever. All right, so we'll do that. Thank you for coming in.